Bien, buenos días a todos. Quisiera agradecer la asistencia y dar la bienvenida a nuestra invitada. Ella es la profesora May Griffith, que es profesora actualmente del Departamento de Oftalmología de la Universidad de Montreal de Canadá. Ella obtuvo el grado de licenciatura y magíster en la Universidad de Toronto, también en Canadá. Luego realizó su doctorado en la misma casa de estudio donde lo obtuvo en el año 1990, el doctorado en anatomía. Posteriormente realizó investigaciones postdoctorales en fisiología, en biología celular del desarrollo en la Universidad de Alberta, en Canadá. Realizó otras investigaciones postdoctorales en fisiología y en anatomía en la Facultad de Medicina de la Universidad de Harvard, en Boston, en Massachusetts, Estados Unidos. Obtuvo un MBA en el año 1997 en la Universidad de Ottawa, lo que le ha permitido combinar sus conocimientos comerciales con los avances científicos que desarrolla en su laboratorio. Gracias a esto ha sido consultora sobre transferencia tecnológica, planificación de investigación y desarrollo y ha realizado asesoría de puesta en marcha de varias organizaciones y empresas. La doctora Griffith es mundialmente conocida por su trabajo pionero en medicina regenerativa, translacional y regeneración de tejidos in situ, de gran importancia en enfermedades oftalmológicas, especialmente de córnea y de retina. La autora, junto con el doctor Per Fagenholm y su respectivo equipo, desarrollaron los primeros implantes corneales biosintéticos sin células en el mundo. Promovieron la regeneración nerviosa y el tejido corneal humano en ensayos clínicos en humanos en Suecia. Posteriormente, la profesora Griffith y el doctor Sangwan completaron un segundo ensayo clínico con implantes corneales biosintéticos que tenían una red de polímeros que suprimen la inflamación en pacientes de alto riesgo. Recientemente, la doctora y su equipo desarrollaron un hidrogel líquido sintético biocompatible y adhesivo que se llama Liquid Cornea para reparar defectos y perforaciones corneales y se aplica como un líquido, pero rápidamente se adhiere y se gelifica dentro de los defectos del tejido corneal. Luego, su similitud a nivel molecular con la estructura del tejido natural promueve la regeneración tisular, tratando las perforaciones corneales de manera efectiva, sin necesidad de trasplante. Actualmente, continúa su trabajo en regeneración de córnea, desarrollando biomateriales biomiméticos para medicina regenerativa a fin de satisfacer necesidades médicas actuales. Gracias a estos trabajos ha recibido variados premios y reconocimientos, además de financiamiento para su investigación por parte de la Universidad de Ottawa, del Natural Science and Engineering Research Council de Canadá y del Canadian Institute for the Health Council Research, también del mismo Canadá. Ha sido reconocida recibiendo la cátedra de investigación en Canadá en biomateriales y células madre en oftalmología, la cátedra de investigación de la Fundación Caroline Durand de la terapia celular del ojo y es directora de la división de córnea de la Red de Investigación de Salud de la Visión en Quebec. Quiero que le demos un gran aplauso y la vamos a recibir y nos va a ilustrar sobre implantes corneales, una visión de futuro sobre la medicina regenerativa de tanta importancia que tiene hoy día en los miles de pacientes que tienen afecciones a córnea y de retina y que la implantación de biomateriales regenerativos le está significando una restauración de la visión a lo largo de todo el mundo, incluyendo Chile. Doctora Griffith, bienvenida a la universidad. La invito a que nos presente su lecture en estos momentos. Quiero que le demos un aplauso a la doctora. Doctora, come here, please. Come here.
Okay, thank you very much for the invitation to be able to speak to you about some of my work. So, just going to tell you a little bit about the university that I'm from. I'm from University of Montreal, and we're the 4th top research university in Canada. We like to think of ourselves as being a very research-intensive place, and so right now we're ranked 111th in the world with 13 faculties. So I belong to the Faculty of Medicine, and this is our university, which is actually nice on top of a hill. And this is Montreal. It's got a lot of nice green space, even though it's one of the largest cities in Canada. So my area is regenerative medicine. And it's basically something that you can't do by yourself. You need to collaborate with people from different areas. You combine biology, chemistry, physics, engineering, and you can see from this picture that just about every part of the body that you find, there is somebody working on regenerating it. So with regenerative medicine, instead of let's say having a wooden leg, somebody's trying to regrow that leg, right? So you can see just about every part of the body which fails. They are trying to regrow it mainly with stem cells. So usually regenerative medicine involves stem cells. And my area is corneal blindness. So as you can see here, it doesn't matter whether you're young, from babies to old people. Corneal diseases affect anybody, and it can be infectious, it can be congenital. Right now, donor cornea transplantation is the only widely accepted treatment, but it's in severe shortage. In Canada, we have about 2,000 to 3,000 people on waiting lists for up to 2 years. And in some parts of the world, you only get 1 out of 70 patients treated. So altogether in the world, there are about 12.7 million people on waiting lists. Now, the other problem is, even if there were lots of corneas, like if they're available everywhere, you still find that there are patients who are high risk that the donor corneas will not help, because these patients will be rejecting the corneas. So each time you reject, you get a new cornea, it will be faster to the next rejection. And that's what I'm trying to work on, a treatment for the patients who will not benefit even from cornea transplants, even if they were available. And 53% of the world's population have no access to corneal transplantation. So there is a big problem and a big unmet need, which is what we're trying to meet with regenerative medicine. Right now, this is what a healthy cornea looks like. It's actually transparent, so you can't see it. What you're seeing here is the pupil, the black hole, and the iris, which is a nice colored part of the eye. And if you look to the sides, you'll see this blue ring. It's a very nice organ to work on, even for research, because the blue ring is where the stem cells are. So if you're looking at stem cell research and you work on the cornea, whether you're working on an animal model or human model, the stem cells are right there. So you can actually use it. And here's a donor cornea. It's sutured on, and the sutures usually stay for about 6 months to a year. And these are two artificial corneas called prostheses. So basically, they are like pinhole cameras. They let the light through the hole, and it gives the patients basically the minimal vision. But they don't look very nice, and there are lots of problems. It's a complicated surgery, and most patients will need antibiotics for the rest of their lives because these things are not, they're not one piece, so they have places where pathogens can go in. So what we wanted to do was something that looks like a human cornea, and this is what we made. And this is the cornea that uses the patient's own cells. So I will be telling you more about that. So the cornea is right in front. It's a simple tissue with an epithelium, a stroma layer, and an endothelial layer. So you can see the structure is quite simple. And most of this is collagen, right? So for tissue engineering, it makes it a lot easier because you can try and replace mostly one thing, which is collagen. Now, for high-risk corneas, most people are working with stem cell transplants. And what they do is they take the stem cells, as I told you, it's a ring around the eye. It's easy to get the stem cells. You culture, you explant, and this is the affected eye, and then you transplant, and you regrow the surface of the eye. The problem is it works better for autologous. So if somebody has a problem with the right eye, you get the cells from the left eye. That works really well. Excuse me. The problem happens when you have allogeneic cells. So if both eyes are affected and you need a transplant and you get a transplant from somebody else, you can see this eye is vascularized, there's lots of blood vessels. The eye itself will reject because these are cells that come from somebody else. And also, if more than one layer is affected, as you see from this picture, it's quite a thick cornea. If it's just the top, you're okay. But if the wound goes below, you still need a transplant. So what we wanted to do was something different. And basically, this is what we made, an implant made of biomaterials. So those of you who are in chemistry, this is a good place to start. So chemistry, biochemistry. We started off with recombinant human collagen. So this uses DNA technology to make a synthetic version of human collagen. And we transplanted the first patients with this material. So what happens is the cells migrate in. These are the stem cells from the patients themselves. They migrate in, they expand, and then they differentiate. And this is the restored cornea. So basically, we are stimulating the patients to regrow their own corneas. And there are several steps from the lab to clinical testing. So the first thing, of course, is you design your new biomaterial. You decide what you need for your material. And then the next thing to do is how you're going to manufacture it. You can use molds, which is what I do. But nowadays, a lot of people are doing 3D printing, so you could also do that. And then we have to check all the physical, mechanical, and chemical properties. So this is where you have colleagues from all the different areas like engineering, physics will help you with these. And we do most of our testing in cells and organ culture in the lab. And then finally, we do in vivo testing, first in mice. And only the very, very best we put into a large animal like a pig. And then we do clinical trials. So this is designing an implant. So we use a lot of biology, chemistry, and physics. Like I mentioned, the first implant we made was recombinant human collagen. So this was using human collagen DNA, put it into a yeast, and they make up the collagen fibrils, and we combined it with a phospholipid. So this is basically a diagram of one of our implants. You mix it, and then this is an implant. It looks like a thick contact lens. There you go. You can see it's like a thick contact lens, and it's quite transparent. And then we test mostly in the lab for compatibility. So this is where most of the work is. And once it's good, we also test other things. So for example, we want to make sure that whatever material we put into the eye, it stays in the eye, it sticks in the eye, it doesn't just pop out. What we do is we test it as patches. So we do bursting pressure. We put the materials into the eye, especially for liquid materials, and then we pump it full of saline, and then we look for the point where it goes whoosh. And these are some people in my lab. This is Dr. Robert. She is a cornea surgeon. And here we are doing bursting pressure testing. This was another postdoc in my lab, and this is Per Fagerholm, a Swedish cornea surgeon. So here he's giving Rabbit an eye exam. We use the same equipment for human patients as we do for the animals, and this is in vivo confocal microscopy. So it's real-time microscopy. And here you can see the allograft with the recombinant human collagen, and this is with our network. And what we do is we check the animals. So here you can see with just an allograft with this high-risk animal model, like alkali burn, you can see it's highly vascularized. So at 1 month, you see all the blood vessels, and even at 9 months, you get the blood vessels. With recombinant human collagen alone, you have blood vessels, but if you put in the MPC to block the vascularization, you can see that the vessels stop at the edge of the implant. And at 9 months, we have vessels here, but here we don't have any vessels. So this is a preclinical study. So before we do any human patients, we always do a study in pigs. And this is the unoperated eye, and here we have 4 mini pigs. So with in vivo confocal microscopy, this is real time. We can look at the cells, we can look at nerves, we can see things going in and out. And this is a pig having an eye exam. We have the surgeon, we have a vet, and this is one of my postdocs. So we have a large team, and this surgery room is just like a surgery room for human patients. So if everything is good, then we work on clinical trials. And to do clinical trials, we make the implants in a certified clean room. So we have a traditional clean room where you wear a spacesuit and you manufacture everything. We also have the non-traditional mini clean rooms where they would be manufacturing things in a clean cupboard. And this is our first trial. Looks like my video is not playing. Oh well. Right. So this was our first in human study. We made the implants that looked like contact lenses. And what the surgeon does is he punches out the damaged area. So this is the damaged area from the patient. I'm not sure why this video is not playing. But anyway, he removes the damaged area, and then he goes to the implant, and he takes out a piece, and it's put into where the patient is, and then we suture it in. So that's basically the transplant. Oh, now it's playing. Interesting. Yeah. So here you can see the surgeon basically making the cut. He's going to take out the patient's cornea. And here you can see it's not a very delicate surgery. You might think that because it's the eye, they are very, very careful. But the cornea is actually very tough. So when we do tissue engineering, we're actually making something that's very, very tough, very, very transparent. And that's the biggest problem, is making it transparent. So you can see he's really, really hacking into it. It's not a delicate surgery like you might think. Let's see if I can control this a little better. So yeah, here you can see that he's taking the final cut to remove the patient's damaged cornea. And then what he will do is to take a piece of actually not equivalent size, but a little bit bigger. And here you can see he has the implant, which is this thing, on this dish, and he is going to cut out the piece that he needs. The circular knife we use is a tree-fine, and here you can see the surgeon has tree-fined out a piece. He's going to pick it up. You can see it looks like a big or thick, rather, contact lens. And this is just put into the hole that he's made in the patient's cornea. And this is going to be just sutured on. It's a little bit bigger so that it makes a tight fit. And here you can see he's making the adjustments and the sutures. So here would be the finished sutures. Yeah, so there you go. And these are the patients. Our first 10 patients were done in Sweden, and that's why you see all the baby blue eyes, because all the Swedes generally have blonde hair and blue eyes. And so all the blue eyes at 2 years, 4 years, and at 8 years. So we followed the patients, and at 8 years, unfortunately, one of the patients was too old and could not come for the surgery. We also had 2 patients whose disease progressed, so they had to be regrafted. However, we had no rejections, so we were very, very happy with that, and you can see, you can follow the trend. We had very, very stable immune-compatible in situ tissue regeneration. Here's a biosynthetic cornea, the human donor, and a healthy cornea. And you can see with the human donors that the nerves are sort of all over the place, whereas a healthy cornea, they're always in parallel lines. And we see this in our biosynthetic. And when you look at the human donor, you see these cells. These are dendritic cells. So these cells are what causes rejection. We see them in a human donor cornea, but we don't see them in the healthy or the biosynthetic. So we're quite pleased with that. And so we started moving to high-risk cases or the very sick eyes. You can see that these do not look very normal at all. Some of them are very opaque with blood vessels. And our second trial was on these high-risk patients. So you can see the before and after pictures. They did well in some cases, and some cases not so well. So in these patients, you can see how red the eye is. These people will not see, even if we transplant them, but we transplanted them to just get rid of the pain, because these patients are blind, but their eyes are still inflamed. And what we did was we patched up the hole, so there's no more hole here and no more hole there. And so these people could not see still, but they are relieved. So 2 to 3 weeks after the transplant, they don't have pain anymore. With the burns and the infection, you can see here the before pictures. You have the big ulcers, and after, we don't get the big ulcers anymore. The infections actually did the best. So this woman had a fungal infection. You can see it left a big scar in the middle. And after the surgery, she had no more scar. She went from 20/800, which is legally blind, to 20/50, which was normal, not perfect, but normal. Means you can drive with glasses. So we're quite happy with that. And when we did our second surgery, we did this at LV Prasad Eye Institute. This is an eye hospital in India, but it's a World Health Organization hospital. And unlike the hospitals in Montreal and in Sweden, they have lots of lasers. So they use the laser for the implant surgery. And this was the woman I showed you. So at 18 months post-op, she was already 20/50, and she stayed 20/50 with normal vision for the rest of the time that we followed her. So that was about 3 years. And here what we did was to actually go one step further, especially even before the pandemic. We were always concerned because when I was in Sweden, we had H1N1 and H5N1. And of course, when that happens, you don't want to have any kind of contamination. So we went from recombinant human to fully synthetic. And so what we did was we made collagen-like peptides. Instead of the long 1,500 amino acid long peptide, we went down to 38 amino acids. And we tested these in pigs. So here you can see the pig corneas. What is different is that we had this MPC. So MPC basically blocks inflammation. And you can see that all the corneas here are clear versus all the corneas here that don't have MPC that are swollen. And here you can see that the implants are quite strong. You can actually play around with them, and we can suture them. So we're hoping that these ones will be in clinical trial later this year, and that will be done in Spain. And then finally, do we really need the solid implants? So we are trying to do something different that would reach the millions of people. And if you have solid implants, that you have surgery rooms, it's not going to happen. So you know from COVID that it's very efficient when you have vaccines, because you just give one patient, 1 or 2 needles, and so this would be the same. These are patients who actually have perforations, so they are basically holes in the cornea. We had lots of perforations, believe me, during COVID because people were not seeing the doctors, and they had perforations. Unfortunately, our things were not ready for clinical trials yet. So here the idea would be that we would inject the liquid into the cornea and it would gel. And here is a pig that had been tested, and this is a pig getting an eye exam. So we look for tear production, and we're doing a slit lamp. So this is with the Schwimmer's test, and this is with the slit lamp. This is Dr. Robert, and she's doing an eye exam on the pig after the transplant. These were pigs that we did before, and this was a rabbit where we actually made a full thickness perforation, and you can see the hole, but after 28 days, the hole is gone. And what we did here is an anterior lamellar keratoplasty, so we basically made a deep hole. And normally what you would do is you would take a cornea and you would transplant it. But here we wanted to see whether we could use a liquid transplant instead of a solid transplant. And what I'm showing you here is, yes, it works. Here's our liquid cornea. Here is a transplant from one animal to another, and an unoperated eye. And you can see that they look the same. The epithelium grows back, the nerves grow back, the stromal cells grow back, and we didn't touch the endothelium, so that was fine. And this is another model with the cats. So pre-op, this is with a perforation. We made a perforation. You can see the different steps. And this is after we filled in the perforation. So this is at 12 months. So pre-op, 1 month, 3 months, and 12 months. So these things work. We did immunohistochemistry. The liquid cornea grew back. The syngeneic graft is there and the unoperated. And this is immunohistochemistry showing that we form a tear film. We have the right markers for the cells. We don't have lymphatics. We don't have a lot of immune cells, except in the graft, because in the graft they generally tend to have more immune cells. But here, because we didn't put any foreign cells, we did not have any immune cells. And of course, the nerves regenerated, so we're quite happy with that. And the nerve densities were good. So to summarize, the human cornea is an example of a simple organ for developing regenerative medicine, and there's also a real need. The biocompatibility is a key. So the host will affect the materials, and the materials will affect the host. So we always try to work on the materials that are more natural. And even though they're fully synthetic, we model it on natural materials, or mostly collagen. And we do most of our testing on cell cultures so that we can avoid animal use. And we only use the animal testing as a final step. And of course, there's a long pathway, but at the end, we have the clinical evaluation. So thank you very much for your time. And this is just to acknowledge the funding sources and multidisciplinary collaborators. So I tend to work with collaborators from different countries around the world, and I hope to be able to add some colleagues from Chile at some point to our project. Thank you.
Stay 1 minute. ¿Alguien quiere hacer alguna pregunta? Las hacen en castellano, esa es la traducción. Doctor Desmond, ¿quiere hacer alguna pregunta? ¿Tiene un micrófono?
Sorry? About these animals. Yeah. That they were not impure to people. That the animals that you use on your experiments already have their burns or already have the so unfortunately, the first animals that we use were mouse models, and we do have to make the burns on them. Same with the pig models, because that's what the regulatory agencies do. But what we're doing is we're working with vets, and we have worked with vets before on using dogs and cats. Well, they're patients. So they already have the eye problems, and we gave them a transplant. So those animals, of course, they already had their eye disease.
Ok. ¿Alguien quiere hacer alguna otra pregunta? ¿Sí? Espérate, te paso el... Tu nombre y tu carrera.
Sí. My name is Oko Emmanuel Godwin. So my question is, I understand that some eye defects are hereditary. And assuming a patient has a hereditary eye, a corneal defect, upon administration of this procedure, is there a chance that such a disease will be permanently corrected or it might reoccur again? Thank you.
Okay, so when I showed you the first clinical transplant, those patients had keratoconus, right? So keratoconus is, I guess, an eye disease that is multifactorial, so it would be like a hereditary one. The transplant basically helped the patients up to about, well, 4 to 8 years. And then when the disease came back, we can give another transplant. What is good with a fully synthetic one is that they behave like new grafts, right? Because each time they are fixed using their own cells, you don't have foreign cells in there.
En Chile, la lista de pacientes esperando un trasplante de córnea es sobre los 1.500 personas. Tiene una lista de espera aquí en promedio para la donación de órganos, donación de córnea, a pesar que ha cambiado por la ley, esperan 3-4 años. Yo tengo una enferma, una paciente mía, que lleva esperando 6 años un trasplante de córnea y su visión cada vez es peor. El tema es súper complicado y esta puede ser una muy buena alternativa a un trasplante.
¿Me paro? Sí. Okay. Actually, I think that it's good morning. No, good afternoon. So there's a way that the patient that born blind can revert that condition. I mean, like, can totally see with those transplants that you are making?
It depends on the condition. So if they're born blind, you know, so this is good for the cornea. It's not good for the retina or optic nerve. So if they're born blind because of like vitamin A deficiency and they have a cloudy cornea, yes, we can fix it. But if they have a hereditary problem like with the retina, this will not do it. So for the retina, we have a different project where we're trying to replace the retina. We should be able to do it in babies, but for clinical trials, we never do it on babies. So for clinical trials, you always do clinical trials on adults because they can give consent. The babies cannot give consent. But once you finish the clinical trials and it's accepted as a treatment, that yes, you can use it on babies as well.
Bien, the last question.
No es una pregunta, sino más bien en respuesta a lo que usted comentó de la necesidad de la donación de córneas. A mí me tocó trabajar en una UCI donde tuvimos a un paciente que fue donante de órganos. El cirujano fue a las 3 de la mañana a hacer la recepción, pero ningún equipo de oftalmólogos se dignó a acusar recibo del llamado que estábamos haciendo para poder rescatar esas 2 córneas. Entonces también no es solamente la falta de donantes, sino que la conciencia en los propios equipos médicos.
I think that is the same problem in Chile and Canada. In Chile, the doctors of ophthalmology don't go to the hospital for the resection in the cornea in cadaveric human body. In Chile, is difficult. Go to the hospital in the eye to the ophthalmology. I think that the same problem in the world because the ophthalmology is very special doctors.
Yeah.
¿Hay alguna otra pregunta? ¿Tú quieres, David? David.
Doctor, when you say about it, there is 23 million of people waiting for, in need for cornea transplant, and you say that only 1 of 70 must access to the treatment. Is there any plan, worldwide plan to diminish this awful number? Because you say that you have a multinational, multidisciplinary collaborators from a lot of countries, but I don't know if they have centers to do the same work that you do.
So, you know, I've been trying to work with a group of people. So when you have more than one group working together, and we tried to partner with, put together a group from India, from the London School of Hygiene and Tropical Medicine. So the idea was with this liquid cornea, we can have everything in a syringe. So it's much easier to be able to treat the people, and you would be able to start to get the millions of people. When you transplant them, each person comes in for a transplant, and there's no way that you would be able to reach the millions. So that's why we actually switched to this liquid cornea, and hopefully we can actually start to target more people that way. And of course we can't do it by ourselves, which is why we've been working with lots of other collaborators around the world, so that we would be able to at least, you know, be able to target some of the groups in need. So we started working with people in Tanzania, in Democratic Republic of Congo, and of course people in India. So once we finish our clinical trials, we should hopefully be able to start treating people.
Okay. Bien. El micrófono, por favor. Ahí sí. Okay. Muchas gracias. Thank you very much. Doctora, quiero que reciba un regalo de parte de la facultad, allá por las medias. Para que tome una fotito, allá. Muchas gracias y un aplauso para... Los invito a tomar un café afuera. Y hay un petit boucher pequeño.